Hi, hello everybody. In today's class, we will discuss about set theory. We will define what a set is, what are the operations that you can do on sets, and given two sets, what are the relationships that exist between any given two sets, and some advancements in set theory. Let us define what a set is. A set is nothing but a structure representing unordered collection of 0 or more distinct elements. Basically, a set is a collection of elements. You can say set of all human beings, set of all guys who registered for MS in bits. This is a set. And when you talk of a set, there is no order that is working on the elements of the set. What I mean is that you can't say that this is the first element, this is the second element, this is the third element, this is the fourth element. That kind of things you can't say it. That is what I mean. We mean by unordered set. And mostly they are all distinct. Even if they are even in set notation, if you write an element more than once, we consider that as one element only. We will see anyway with an example. And why we need set theory? Set theory is going to be ubiquitous in computer science. Wherever you go, it is going to be there. You have to prove anything, it is going to be there. And as a data structure also, it is going to be there in most of the programming languages. And in mathematics or in theoretical computer science, whenever you want to prove anything, most of the things have been defined in terms of some form of set theory. How the things will be defined is basically they take a set and they apply a predicate, and they say that all the elements who satisfy a given predicate constitute a set. That is what they say generally. We will see with an example. That is why we are interested in studying set theory. Though some of the things today I teach will be known to you in your prior education, in graduation and intermediate or whatever it is. Let us revisit or redo the things for the sake of completeness. If you miss anything, you can catch it here. This naive set theory is the fundamental set theory. People first came up with the naive set theory. Here it is defined as any collection or class of objects that we can describe, probably however, whatsoever, and whichsoever you can describe the set of objects that constitute a set. That is how it is defined. If you are able to define a set of objects, it constitute, you will get a set out of it. That is how it is defined. But unfortunately, what happened, the naive set theory is the fundamental set theory that we had with the definition of how a set can be defined. You will have people came across after some time, people were having some propositions which are true and which are false at a given point of time, at the same point of time. As obviously, whenever you have got a theory, you are going to define some things and you will have some set of axioms. In the similar way, this naive set theory also has some definitions how we define a set, and it is having, they lay down some axioms. With these kind of axioms, with kind of definitions, over the time what people discovered is, with these kind of axioms in place, they are able to find a proposition, a statement which is true and which is false at the same point of time, which makes this whole theory, the naive set theory, an inconsistent system. Then people came up with some axioms be added in naive set theory and make the whole system a consistent one. That is how people have solved this problem. You have got some axioms in naive set theory and you have got some definitions With that the problem was, you got some propositions which are true and false at the same point of time, which is not okay. The whole theory has become inconsistent. To beat this out, guys, people basically, they have come up, they have put some more axioms into it, and they made some definitions more formal, more better, so that the theory is consistent. That is called ZFC set theory and all those things. However, we will study only naive set theory for this course, because whatever we define in naive set theory still is holding good in the ZFC theory or higher or the further advancements of the set theory. Whatever we prove, they still hold good in the higher orders of the set theory, and definitions still hold good, and what basically we need is being satisfied by naive set theory. So we will study only naive set theory, but remember, it is inconsistent. There is a higher, there are better set theories which we have no inconsistency as of today, and whatever we speak will still hold good in the other versions of set theory. So let us get into actual set theory now. Basically, any set will be defined by capital letters, STU, that is how you call a set, and generally the elements will be denoted by small letters. However, it is not mandatory. And you can define set theory in another way also, that is people call builder notation. How it is going to work is, basically you define a predicate. You know what a predicate is, isn't it? Px is a predicate. I can define Px, a predicate, something like x is a prime number, and I say the universe of this x is set of natural numbers. I can say like this. X is a prime number, and universe of discourse is set of natural numbers. I mean n by set of natural numbers. I can define this predicate. Then the set that I am going to define is set of all x for which Px is true. Can I do it or not? I have defined a predicate called Px, which is nothing but x is a prime number, and universe of discourse happen to be set of natural numbers. Then the set is basically defined like this: set of all x such that Px, when I say Px, it means Px is true. So what do I get? Set of all prime numbers, something like this: 2, 3, 5, 7, and all these things. This is equivalently, set of all prime numbers is equivalently defined as set of all x Px, where Px is a predicate that has been defined as x is a prime number. This is another way of defining a set. Inherently, all the elements that are there inside the set are unordered. What I mean by this is, say if I have got a simple set called S is equal to ABC, that means it is having 3 objects inside it. Then however you represent this particular set, you represent it by ABC or ACB or BAC or BCA or CAB or CBA, they are all one and the same. They all represent only one set, that is S. And all elements inside a set are distinct. You can write an element n number of times, but actually it makes no difference. Suppose in the same set S, if I have got A is equal to B, then you can write the set ABC as AC or BC, or you can write A n number of times. Really the whole set means the set AC, the same set AC. So you can repeat an element n number of times, but in set, it doesn't make any difference. It represents the same set with only one time writing that particular element. And if you have got two sets S and T, we will say these two sets will be equal if and only if they have exactly the same number of exactly the same elements. Just take this particular example. Consider a set 1, 2, 3, 4 and consider another set like set of all x such that x is an integer where x greater than 0 and x less than 5. This is another set. If you see actually the way they have been described, this is another set. And look at another set definition, that is set of all x such that x is positive integer whose square is greater than 0 and whose square is less than 25. This is another description. But if actually you look at the elements that have been laid down by this particular definition are the same, that is 1, 2, 3, 4. So they syntactically be defined in three different ways, they represent the same set, that is 1, 2, 3, 4. However you describe, as long as all the elements in one set are there in the other set and all the elements that are there in the other set are there in the original set, the two sets will be equal. The description really doesn't matter as long as the objects inside the set are the same. And infinite sets, this is very interesting for us, especially for computer science guys. I mean, a set is a finite if a set is a finite set if the number of elements inside that set are finite. When I say finite, it can be 100, it can be 10,000, it can be 1 billion. All these are finite sets. Infinite sets is, I mean, you will not be able to say how many actual number of elements that are there in the set. They are infinite. This is all fine. We all know what infinite sets are. Set of natural numbers is an infinite set. You really don't know how many elements are going to be there in that particular set. Similarly, set of integers, set of real numbers, all these things are really infinite sets. But as computer science students, what we are interested in is a set can be infinite, but what we are interested in is it countably infinite or uncountably infinite. This is very interesting. And a set can be infinite, but will I be able to take an element from the set and give a rank to it, so that this is 100th element of the set, or this is 1000th element of the set, or this is 9500th element of the set. Can I cook up a function such that I can give a rank to each element of the set? If I am able to do it, though the set is infinite, I say the set is countably infinite. I am able to count I am able to give a rank to each element of the set. This is actually not the right place to speak about this, but let me spend 2 minutes on it. If you remember what a function is, which I am going to cover in the next class, I will say if you come, I got a set S which is infinite set, I will say this set S is countably infinite set if I can cook up a function such that I can have a bijection from natural numbers to this set. I will cover it anyway in the next slide, in the next class. What I am saying here is basically I have got a set S and it is an infinite set. When I can formally it is defined like this, when I can say this particular set and this set a countably infinite set, it is defined as if you can cook up a function f which is which is working from, if I can cook up a function, f such that it is defined from s to n and it is both 1 1 and on 2 at the same point of time, then I can say this set S is countably infinite. Otherwise I cannot say this is countably infinite. It is going to be uncountably infinite. Only one thing we have to do, given a set which is infinite, if I am able to cook up a function such that there is a bijection, that is 1 1 and on 2 from itself to the set of natural numbers, I call it I call this particular set a countable set, countably infinite set. Otherwise I say it is uncountably infinite set. This is interesting for computer science people because we all deal with countable things. When you write a program and when it goes to infinite loop, it definitely goes to an infinite loop, but at any point of time you will be able to say which iteration of the loop is running. This is 78,000th iteration is going now, 1,25,000th iteration is going now. Like that you will be able to say, in spite of it being an infinite loop, you will be able to give a rank to each iteration. So hence it is countably infinite. We all deal with basically countable sets, be it finite or infinite. When basically you do theory of computation and all this, very much helpful. Get this. And we say when you have got an element and which that is there in the set, we generally represent it by the symbol belongs to. We say x belongs to S means that x is an element of C. We say 3 belongs to N because 3 as a number, it belongs to set of natural numbers. And if you see with this particular notation, let us see how we can define two sets are equal. We say two sets S and T are equal. This is all we know. This is if and only if. You take any element in S, that is x, you take any element of S, that element should be there in T. What I mean here is, take any element of x in S, that should imply the same element should be there in T as well. And similarly, you take any element in T, that element should be there in S as well. When these two conditions are happening, then I say the two sets are equal, otherwise not. Okay, when x, this particular notation says that x does not belongs to S. This is a notation, just a notation. When we say that this element is not part of this set, notationally we will write like this. And null set is the unique set that it contains no element whatsoever. It is a set, but it does not contain any elements. And this is an axiom. I told you now that any theory will have some set of axioms there, and based on the axioms you are going to prove some theorems. One of the axioms in set theory happens to be not this particular thing. What does it mean in predicate logic? There exists x belongs to empty. There exists an element x such that x belongs to this particular set called empty set. It should be false. That is what this guy means, isn't it? Not of there exists x belongs to empty set. How to understand is, first without not you understand this. What does this mean? There is an element x that is there in the set empty set. This should not happen. That means there should not be any element there in the empty set. This is how it is defined. Don't worry about it. This definition, you just get it. how and all we should not ask, this is how it is defined. Now, when you have got two sets, one set can be a subset of T. We can define a set is subset of T whenever all the elements in S are going to be in T as well. Then we say S is subset of T. Equivalently saying, this is the great use of the logic that we have studied, isn't it? For all x, whenever x belongs to S, then that element should be there in T also. Whenever this particular condition is being satisfied for all x, then I say S is subset of T, otherwise not. Hope you are getting me. If you take this particular definition, it is obvious to see that empty set is subset of S, because if there is an element in empty set, then I need to show that that element has to be there in set S, but empty set does not have any element, so that statement still holds good. Hence, empty set is subset of S holds good. Similarly, we can see S is subset of S. You take any element S that is going to be there in S by the very definition of the S. Hence, S is subset of S. And similarly, we can define S is superset of T. That means it's just saying that T is subset of S. Now, obviously, when you have got two sets S and T, and to show that they are equal, it is sufficient to show that S is subset of T and S is superset of T at a given point of time. If you can say that, then both sets are going to be equal. It is in fact necessary also. What I mean here is, you have got two sets, they may be syntactically different. Two sets, the way they will be defined is different. These two sets will be equal if and only if one set is subset of the second set and second set is the subset of the first set. If you have got this particular condition, then the two sets will be equal and vice versa. And when I say generally S is subset of T, S is subset of T, S can be T as well, isn't it? That is what we have seen in the last slide, that S is subset of S. But to beat this out, basically, proper subset actually beats this out. When we say S is proper subset, that means subset, this is not going to be there in case of proper subset. S is subset of T means basically all the elements of S are going to be in T, but there exists at least one element in T that is not there in S, that makes it proper. For example, you have got a set 1 2 3, you have got another set 1 2. 1 2 is proper subset of 1 2 3 because there exists an element which is not there here. Hence, it is a proper subset. Diagrammatically, if you have to understand this, if this is a set T, if this is a set T, and if this is a set S, that means there exists an element here which is there in T but not in S, then we say S is proper subset of T, otherwise not. And when we define set, objects of a set can be set itself. So basically, when we have got a set, the elements of the set we call objects, isn't it? And these objects themselves can be sets. We will see with a small example. Can I define a set like this or not? Set of all S such that set of all X such that X is a subset of the set 1 2 3. Can I define a set by this or not? Yes, very much. The very definition of set makes us to define set like this. So, what are all the elements of this set are going to be? I have got a set 1, 2, 3. How I define my set, how I am describing my set is any subset of this guy is going to be the member of my set S. So, what are the subsets over here? The obvious subset is empty set, isn't it? Empty set in fact is a great set. It is going to be it is subset of any set whatever you can define in the universe. So, definitely empty set is going to be a member of my set S. That is why I have written empty over here, empty set over here. The another subsets I can see is the set containing only 1, the set containing only 2, the set containing only 3, the set containing 1 2, 1 3, 2 3 and 1 2 3. All these are subsets of 1 2 3. Hence, my S is this set. Isn't it? I have got a set in which the members are themselves sets. Okay? And only one small observation is when you have written 1 and curly bracket 1 and curly bracket 1, they are not the same in this notation because this is an element 1. This is a set probably actually containing the element 1, and this is a set which is containing another set, and that set is having 1 as its element. Hence, these three are distinct by the very definition. This is just an element, this is just a set, and this is a set containing another set as its element. They are not the same. There is just an observation. Then cardinality. The cardinality is very simple. You have got a set S. Just count the number of elements that are there inside this set S. That number is called the cardinality of S. As simple as this. Now, our obvious set, the empty set. What is the cardinality of empty set? I have to count the number of elements in the empty set. Actually, there are no elements. Hence, the cardinality of the empty set is 0. And if I consider 1, 2, 3 as the set, what is the cardinality of this set? It is going to be 3 because there are 3 elements inside that set. If I consider another set having A and B as its element, cardinality is going to be 2. There is no confusion over here. Though you know all these things, just get this notation because this notation is what we are going to use in higher studies of our computer science. Right notation is also equally important. Now, I will just ask you, what is the cardinality of this particular set? My set here happens to be 1, 2, 3, comma 4, 5. What is the cardinality of this set? Just think a minute. Is it 5? No, because this set is having 2 elements. One element is the set 1, 2, 3, another element is the set for 4, 5. It is having 2 elements as its members, which are in turn the sets. Whether they are sets or not sets is immaterial to us. How many elements are there in the set is what is important. If you ask me how many elements on this particular set, I say 2 elements. One element happens to be a set, another element happens to be another set. As I told, finite and infinite, if the cardinality of a set is a natural number, we say it is finite, otherwise it is infinite. We have seen lots of infinite sets. Generally, set of natural numbers is being denoted as this particular thing. this particular notation. This is n only, but there will be another line comes. This is how set of integers will be represented. This is how set of real numbers will be defined, will be denoted, and all these happen to be infinite sets. And power set notation, you have got any set, say you have got a set AB, this is a set, AB is the set that you have got. Power set of set is nothing but generally denoted like this, generally is the set of all subsets of this particular set, that is called power set of S. So, if I ask you to write down what are all the subsets of this particular set in our example, we will write definitely empty set, set containing A, set containing B, and set containing AB. These are all elements of the set. So, power set is nothing but a set which is containing all subsets of the set S, that is called a power set. People write it 2 power S also, this is a notation. And obviously, given a finite set, you have got a finite set S, how many, and say cardinality of S happens to be say a number n, then it is a 10th class problem to find out how many subsets of S will be there. 2 power n subsets are going to be there. It is a permutation combination problem. Given a set, how many subsets are going to be there? 2 power n. So, if the set happens to be finite, the cardinality of the power set is going to be 2 power mod s, where mod s is the cardinality of the set S. We just had some notations about set theory. As I told, naive set theory is inconsistent. Why? Because the very definition of set theory and some axioms laid down will enable us to define sets like this. Look at this set. S is defined as set of all x such that x does not belongs to x. They may they actually don't exist, but will set theory will enable you to define a set like this or not. S, it enables you. So, you can define a set like this. I define a set like x such that x does not belong to x. Now, look at this particular proposition, S belongs to S. If you say S belongs to S, S belongs to S, yes, the element S is going to be in S. Because it is there in S, you get that S does not belong to S. And if you take S does not belongs to S, then S belongs to S, because S does not belongs to S means S belongs to S. This is the inconsistency that we have been talking. You really can't say the truth value of this. You can argue in both ways. That is where we are stuck. That is where this theory is stuck. You got a statement for which you can't decide the truth value, and it is very much a declarative sentence. It is a preposition. You should be able to do it. This has been coined by Bertrand Russell, that this particular naive set theory is going to have this kind of inconsistency. There are some statements like this which will make this theory, this naive set theory, a inconsistent one. And as I told you previously, we don't worry about it, because we still go ahead with naive set theory, and whatever we are speaking is going to be true in the higher order of set theory also. And what we need is being brought to us by naive set theory. what we prove is definitely we can the same things even still hold good in higher orders also. Ordered n tuples. I mean these n tuples, you should be knowing this when you study Euclidean geometry and all those things. They are all tuples basically. They are nothing but sets. The only difference here being there is an order that is working on the elements of the set. You can say this is the first element, this is the second element, this is the third element, this is the fourth element. Like that you will be able to say. And duplicates do matter here. That means when I say 3, 4, 5, 5, 3, when I say this is an ordered tuple, this is not going to be equal to 3, 4, 5. This is different and this is different. But if you consider the same with the same set of elements, the set you get here out is 3, 4, 5, 5, 3. This is one set, and another set is, say this set is, you can write it as 3, 4, 5. There are two sets, but by the very definition of set theory, we say that though you are seeing two sets here, they are actually the one set, and that set is 3, 4, 5. That is what we say in set theory. But in ordered tuple, it is not the case. When you have got an ordered tuple like 3, 4, 5, 5, 3, it is not going to be the same as 3, 4, 5. Duplicates do matter over here. And in set theory, you have got this luxury. You can write 1, 2 and you can write 2, 1. Both sets are going to be equal, isn't it? In set theory, in sets this is going to be true. These two sets are one and the same. But in ordered tuple, you write 1, 2 and you write 2, 1. They are not going to be the same. They are two different ordered tuples. The best example for ordered tuple is two-dimensional geometry that you already know. The point 1, 2 is an ordered tuple. If you have got geometry, I mean this is 1 and this is 2. So this is the point 1, 2. And 2, 1 is going to be somewhere like this, somewhere here. These two are definitely different. So all the set of the Euclidean geometry is the points that you speak there are ordered tuples. They are also inherently the sets, but some more conditions have been put on them, like ordered and duplicates do matter and all these things. And given two sets, you can define a Cartesian product. If you have got two sets like AB and 1, 2, the Cartesian product is basically defined as take one element from here, another element here, then the resultant tuple is going to be there in the Cartesian product. Basically it is defined like this: A cross B is defined as set of all A comma B, where A is taken from the set A and small b is taken from the set B. And basically that means A cross B is going to contain ordered tuples, one element from the set A and another element from the set B. It is but obvious to find out that how many number of elements are going to be there in the set A cross B. Again, if you carefully observe, A cross B is going to be a set again, isn't it? It is a set of ordered tuples where each tuple contains first element from A and second element from B. So hence this is obviously a set. So what is the cardinality of this set? That means how many elements are going to be there in this set? It is going to be cardinality of A, the number of elements in A multiplied by the number of elements in B. This is obvious, because for each element, say A1 is an element of A, then in how many tuples that it is going to be present in? For each element of B, it is going to get one tuple. So how many such elements are there in B? Cardinality of B elements are there. So for one element you are going to get cardinality of B elements. So how many elements are there in A? Capital cardinality of A. So the total number of elements are going to be A and B. That is how you can derive that the cardinality of A cross B is same as cardinality of A and cardinality of B. And we can extend this to any number. And we all know how the union operator works across two sets. If you got two sets, basically A and B, A union B is defined as set of all elements X such that the element should be either in A or in B or in both. Then all such elements you put them in A union B, and maybe the symbol is coming from that U only, might be that when you say A union B, this is nothing but the union that we spoke, the first letter of the union, that is U. And it is interesting to observe that if you got A and B, when you think of the sets which contain both A and B, there can be a number of sets. Among all those sets, A union B is going to be the smallest superset. There cannot be any subset of A union B which is containing both A and B. It is just an observation. If A, B, C union 2, 3 as test sets, we will get this. And this is easy to see it. Though you write this way, this is actually same as this, and this is how we write most of the times. What I mean here is, if you really represent them by some diagram, 2, 3, 5 is going to be in one set and 3, 5, 7 is going to be in another set. The union of this, just write all these elements. Similarly, the intersection. If an element is going to be there in both the sets A and B, then that element is going to be there in A intersection B. This is how it is defined. And if you can see, if you really understand this particular definition, you will be able to appreciate the simple fact that A intersection B is going to be subset of A, isn't it? And A intersection B is going to be subset of B, isn't it? But the only one quality this A intersection B is having, it is the largest subset which is contained in both A and B. There may be n number of sets which are contained in both A and B. Among all those sets, A intersection B is the largest set. So, if you got two sets like ABC intersection 2, 3, what is the intersection over here? Just imagine, just think. It is going to be an empty set because there is no element common, and in this case it is 4. And disjointedness, we say two sets are disjoint if their intersection is empty, they do not have any element in common. For example, like this this guy has been disjointed, his hands is disjointed from his head and all his organs have been disjointed from each other. So, we will say this guy is disjointed. And this inclusion principle, the cardinality of A union B is same as cardinality of A plus cardinality of B minus cardinality of A intersection B. So, basically here we are counting the elements that are there in common between A and B twice, isn't it? So we have to take in common things out to get actual sum, and the complement difference of a set has been defined like this. If you got two sets A and B, if you got two sets A and B, the set difference A minus B is defined as a set of elements such that X should be there in A and that element should not be there in the set B. All such elements are going to be part of this set, that is A minus B. A minus B typically contains all the elements that are there in A but not in B. Such set is A minus B. This is what the definition of the thing is. Set of all X such that X belongs to A and X does not belong to B. And equivalently you can write like this also. So if you have got set 1, 2, 3, 4, 5, 6 and when you subtract 2, 3, 5, 7, 9, 11 from that, what you get is, so because 1 is here and 1 is not anywhere in the other set, so 1 is going to be there in the set. 2 is here and 2 is here also, so 2 is not going to be there in the subtracted set. 3 is going to be there, so 2 is not going to be there. 3 is here and 3 is here as well, so 3 is not going to be there. 5 is here and 5 is there also, so 5 is not going to be there. So 1, 4, 6 are going to be in the set A minus B. And if you see, if you negate set of all natural numbers from set of all integers, what you get is set of all negative integers. So basically you got set represented by this and set represented by this. There are some common elements. A minus B may what you get is this portion is A minus B. It takes a byte out of A and that byte will not have any element of B. That is what byte means here. And say you got a universe of discourse. Whenever you say universe of discourse, it is always a set. Even when I say in predicate logic, I say that the variables derive their values from the universe of discourse. When I mean that actually universe of discourse is the set, when I took the example of the predicate Px, I took this in the before last class, such that X is sleeping. When I took this example, I say that universe of discourse for X happen to be human beings. So here the universe of discourse is nothing but set of all human beings, isn't it? So whenever you got a universe of discourse, is nothing but a set actually. So when you got a universe of discourse, it is defined properly, and you got a subset of this guy. A is subset of U. Then complement of A is defined as all the elements in the universe of discourse that are not there in A, U minus A. When universe of discourse happens to be set of natural numbers, and what is the complement of 3, 5? All the natural numbers excepting 3 and 5. You got universe of discourse. This blue portion is all universe of discourse, and it is containing a set called A. Then A bar basically represents all the blue portion negating or subtracting the yellow portion. All this is A bar. This is called definite complement. And as we have seen, having known all these things, there are some identities. A union empty set is A, and A intersection the universe of discourse is again A. A union universe of discourse, that is U, is universe of discourse. It is always like universe of discourse is there, and A is a subset of universe of discourse. With reference to some context, we define universe of discourse, and all the sets are actually part of or subsets of this universe of discourse. And when you have got this premises, A union universe of discourse is U, and A intersection empty set is empty set. Now idempotent law is this: A intersection A is A, and A union A is A. Double complement, you got A's complement is this. What is the complement of this particular set? It will be again A, and these union and intersection are commutative. What I mean by commutative is A union B is same as B union A, absolutely no difference, they both represent the same set, and they are associative as well. That what I mean is A union B union C is same as A union B union C. These are all identities, these are all you can use as and when you require it, they are all correct, you can prove it also. And De Morgan's law, whatever we have seen in prepositions, most of the laws here are there as well. And similar to that, what is the complement of A union B? It is A complement intersection B complement. And what is the complement of the set A intersection B? It is complement of A union complement of B. Okay. So now we will see how the identities like above, or any identities in set theory whatsoever, whatever the identities that we want to prove, how do we prove the identities are basically given two sets like E1 and E2. You have to show that they are equal. Then one methodology says that show E1 is subset of E2 and E2 is subset of E1. This is one way, somehow you show, how you show is up to you. And then another way to show is take an element of E1 and show that element is going to be there in E2 also, and similarly take an element of E2 and show that element is going to be in E1 also. If you are able to show that both sets will be equal. This is so obvious, I do not spend much of time over here. This is an easy exam, and this is an example that generally we do it in 10+1 or 10th standards. I mean, how do you show this particular identity? You take an element from this set. First you show that this particular set that is on the left hand side is subset of the right hand side set, and vice versa. That means the right hand side set is subset of the left hand side set, then both sets will be equal. We will just take one simple portion. We will take an element from the left hand side portion and then show this element x is going to be there on the right hand set also. When we know x belongs to A and x belongs to B union C, it means that x is in A and either x is in B or x is in C. This is what exactly it means when I say that x belongs to A intersection B union C. Then we have got two cases here. We will show that if it x belongs to B, then we show that this x is going to be there in the right hand side set, and in another case if x belongs to C, then also the x is going to be there in the right hand side set. Then in all the cases we have shown that this x is going to be there in the right hand set. If x belongs to B and x is already there in A, so you can write x belongs to A intersection B. When x belongs to A intersection B, then definitely that is going to be there in this set, because that is there in the set, it is immaterial whether it is there or not, this is going to be there in this set. Hence x is going to be in this set. with a similar argument x is going to be there in this set as well. Hence x is going to be there in the set in both the cases. Hence left hand side set is subset of right hand side set, and with the similar argument of the basic definition that we have got, we can prove the right hand side set is also subset of left hand side set, and thus we can prove it. And this union operator, as of we have seen, it looks like a binary operator. That means union operator you can talk on two sets, A union B, S union T, like that. But actually it can be an n-ary union or n-ary operator also. It can actually, you take union of n sets. Okay, you can union n number of sets. For that matter, you can union infinitely many number of sets also. And the beauty of this commutative and associative property is where you put the order and grouping is irrelevant. How do you group is really irrelevant. Finally you get the same answer. What I mean is A1 union A2 union A3, whether you consider this set or this set, they are really going to be the same because of the virtue of associative property. Generally it is also represented as union of n sets as I runs from 1 to n ai, or for infinite sets you can always write A belongs to x, where this x is containing all sets. Union of all such sets can well be represented like this also. In the similar way, the grouping and order is very much irrelevant in case of intersections also. You can also talk intersections for finite number of sets and infinite number of sets. The beauty of this course is, can we represent one in terms of the other, one discrete structure using another discrete structure? Yes, we can represent it. Set of natural numbers is a discrete structure because basically it is a countable set, countably infinite set. You can represent set of natural numbers by, can represent by 0 by the set empty set. You can represent this number by the set containing the 0th element, and you can represent the natural number 2 by the subset containing 0, 1, and that is how, given any natural number, I will be able to represent that natural number in terms of a set. And more interestingly, all these natural numbers, they can be represented in terms of bit strings, isn't it? 0 is represented as 0, 3 is represented as 1 1, which is a bit string. Bit string, what I mean is a string which is containing bits as its values. What I mean here is this is 1 0 1 1 1 0. This is a bit string because it is a string which is containing only 0 and 1 as its values. 4 can be represented as 1 0 0. That means all natural numbers can be represented as bit strings. And with this we will conclude this lecture. This is very interesting. If you have got a set, let us come back to example first. Let us go to example first. If you have got a set and that set there is some order working on the set, the example that we can take is set of natural numbers. There is an order on the set, basically. Then you consider a subset called as 2 3 5 7 11. Then actually this set can be represented as a bit string. You know how it is? You just take a string of 11 characters. Yeah, to represent this particular subset in terms of bit string, how we will do is consider a bit string of length 11 and look at this. The first bit represents 1, whether the element called 1 is here in this set or not. The natural number n, the natural number 1 is there or not in this set. It is not there, so put 0 over here. The second natural number called 2 is there in this set or not. It is there, so put 1 over here. 3, it is there, so put 1 over here. 4, it is not there, put 0 over here. 5, it is there, put 1 over here. Like that, this set can be represented as bit string, isn't it? Given any finite set in natural numbers, that finite set can be equivalently represented as bit string. For example, 2, 3, 5, 7, 11 will be represented as 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1. The simple thing I have done is, this position is for natural number 1, this position is for natural number 2, this position is for natural number 3. And what is the maximum number? Till that I go 11. And if that natural number is there in my set which I want to represent it in bit string, I will keep 1, otherwise I will keep 0. 1 is not there, so I put 0. Sorry, 0 is not, I start with 0. 0 is not there, so I put 0 here. 1 is not there, so I put 0 here. 2 is there, so I put 1 over here. 3 is there, so I put 1 over here. 4 is not there, so I put 0 over here. This is how I represent a subset of a set by bit strings. Of course, there are some conditions that are to be there, that the basic set has to be, some order has to be there and all. Now, the beauty of all these things is, I have got a set like this, and I have got some other set like 1, 3, 4, and obviously this also can be represented like this. And the union and intersection and complement of all these sets are the same operations, or can be derived from the bit string operations that we have seen some time back. 2-3 lectures back, we have seen this bit string operations, how operations work on 2 bit strings. So you have got, say, this is the bit string for this, and say there is another bit string like 0, 1, 0, 1 is there, I put 1, 2 is not there, so I put 0, 3 is there, I put 1, 4 is there, I put 1, so 5 is not there, 6 is not there, 7 is not there, 8 is not there, 9 is not there, 10 is not there, 11 is not there. This is the equivalent bit string for 1, 3, 4, and bit string for 2, 3, 5, 7, 11 is this. So you want to know the union of these sets is same as bitwise OR operator that is working upon these 2 bit strings. You just apply bitwise OR operator on these 2 strings, the resultant bit string you will get, isn't it? The equivalent representation of that bit string is the union of the set S and T. The set of what I mean here is the set operators union is nothing but the bitwise OR operator that is working on bit strings, if you represent this particular way. Intersection is same as bitwise AND operator, and complement is equivalent to NOT operator. Either you do union in subsets or you do bitwise OR on the bit string representation of the subsets, the results are same in their own representation. Okay, this is how we have seen set theory, what basically we need in computer science, what are the basics that we need computer science, we have seen it. Okay, next class we will see functions. Okay, bye, thanks everybody.